Good afternoon, everybody. My name is Mike Hadlow. I've come here from the UK today. I live in a little town called Brighton on the south coast. It's very nice. If you're ever in the UK, come and pay us a visit. Today, I'm going to be talking about monads. Who here knows what a monad is? Okay. Who here has heard the word monad but doesn't really know what it is? Okay, well, this talk is for you guys. Yeah. Who here is here because they've never heard the word monad before and are just kind of curious? Okay, well, possibly for you guys too. So that's nice. I think if you eat Y combinators for breakfast and you're a category theory guru, then you're going to find this incredibly low level and slightly dull. But what I wanted to do with this talk was to sort of take you on a very, very quick version of a journey that I've been on myself over the last year to 18 months, well, a couple of years, I guess, is that I got very excited by functional programming with the new features in C#3 and LINQ. And I started hearing things like monads and applicative functors and all these kind of like category theory words, and started trying to find out what they meant. And I found it very, very difficult to get a kind of intuitive grasp of what it was all about. And very difficult to get examples in a language that I understood, C#. So the aim of this talk is to put together a nice brief introduction in C# into monads so that people coming on the same route that I was on can find it easier to get up to speed with them. Okay. So, what are we going to be talking about today? Well, first of all, I'm going to tell you what a monad is, but as you'll probably find, as when I did, is that just hearing what they are often isn't enough. It doesn't give you enough really insight to sort of start using them. A very brief history of monads, and this is mainly to dispel some misunderstandings or some sort of false turns you can take if you start to research them. We're going to spend most of the talk coding in C#. And then right at the end, we're going to have a very brief kind of comparison of C# versus F# versus Haskell and the way they treat monads. If you want to follow along, the code for the talk is here on GitHub. Or in any case, you can grab that later. I think the slides are going to be distributed, aren't they? So, okay. Right. So, monads. Before I try and describe what a monad is, I want to introduce this concept of an amplified type. Now, I've just I didn't invent this word, but it's kind of an invented word. What I'm talking about here is a type with a single generic parameter, like IEnumerable of t, a list of t, a nullable of t, and a task of t. I quite like the word amplified type because it's as if these amplified types take a simple type, like a string or an int or a datetime or one of your own types, and give it superpowers. Yeah, so these are like superheroes of types. So an IEnumerable of t, for example, an IEnumerable of string isn't just a string, it's a pipeline of strings. It's a string with superpowers. And an iList of int isn't just an int, it's a whole collection of ints. A nullable of int is an int that might not be there. It's got that kind of magical power of not being there sometimes. And a task of string has got the superpower of not being here now, but only being there in the future. So they all provide extra facilities around basic types, yeah? Wrapping and enhancing them. But there's a drawback. Whenever we use one of these amplified types, we always find ourselves writing boilerplate code around them. And the boilerplate code always looks the same for the particular amplified type. So it leads to very repetitive coding. So if I'm going to be programming with an enumerable of t, enumerable of string, say, yeah, I'm going to be writing a for each loop. Yeah? And if I've got an enumerable of t inside an enumerable of an enumerable or something, then I would have sort of nested for each loops. The same for iList. If I'm programming with nullable int, then I will be writing a conditional first, if has value, and only then accessing the wrapped value of the nullable. Yeah? And of course, for the task of t, I have to use some kind of continuation passing thing, continue with, in order to get at the wrapped value. So they all come with boilerplate. So what monads allow us to do is to take that boilerplate that comes with these amplified types and wrap it away and put it away somewhere so we don't have to worry about it again. And we can program using amplified types in a very natural way, as if we were dealing with simplified types, or almost as if we were dealing with simple types. Yeah. So a monad is simply one of these amplified types. So that's just a type with a single generic parameter, yeah? And we implement two methods. A toWhatever method, yeah? So toEnumerable, toNullable, and a method called bind. Bind is the kind of the more interesting of the two, because that's where we put the boilerplate code that comes along with our amplified type. It's got that rather scary signature for a good reason, and we'll see when we look at the code that sort of the crazy signature there actually falls very naturally out of doing function composition with monads. Yeah. So monads are very simple. They're not scary at all. It's just a type with a generic parameter that implements these two methods. And by implementing these two methods, as we'll see when we look at the code, we can then compose functions in terms of the monadic type in a very, very nice, elegant way. Okay, so now I want to talk a bit about the history of monads. Like I said, mainly to sort of dispel some misconceptions. So maths, lots of really scary maths, far too scary for me. I mean, I've got sort of quite good high school maths, I guess, but that's about it. And you know, I've watched a few videos on YouTube of category theorists sort of talking about monads and things, and it's like me listening to Danish. I didn't understand a word. So yes, I'm sure if you do understand category theory, that you'll have a much more profound and subtle understanding of the concept of monads. Of course you will. You know, you'll understand it more deeply. But my point today is that you don't need to understand the category theory in order to use monads as a practical pattern in programming. So when you start researching monads, you type monad into Google, and up comes a load of stuff about category theory and some really scary maths. Don't worry, you can kind of ignore that and go and sort of and look for the actual programming bits. Although if you can understand it, that's great. So how do we come to be using monads in programming? Well, monads came to programming via a programming language called Haskell. Are there any Haskell programmers here? Yeah, a couple, yeah. It's a fascinating language. I've been making some efforts to learn it myself over the last sort of year or so. It's an academic research language, I guess. It comes out of academia. And it was basically the sort of a bringing together of several separate strands in sort of pure functional programming languages. And it's used as a sort of test bed for a lot of new ideas in programming. Now, if you've got a pure lazy functional programming language, that's a language that has no side effects and no guaranteed order of execution. Yeah? It's, in fact, simply an expression. So this is a problem. If I'm writing a useful application using a pure functional programming language, if I want it to do I/O, if I want it to put something on the screen, then of course it's causing side effects. It's causing side effects on the screen. And if I want to type into my pure lazy functional program, then I'm changing its state, which obviously isn't allowed. So there's a problem here for the designers of pure lazy functional programming languages. And Haskell, as I understand it, initially had a kind of a rather sort of nasty hack around this in order to deal with the I/O issue. But then monads were introduced by these guys as a way to wrap up the parts of the Haskell program that were imperative and had mutable state from the parts of the program that weren't. And it turned out that monads were a very nice abstraction for doing those kinds of things. One of the properties of monads is that they act as a kind of marker, so that if your function returns a monadic type, it can tell you things about what that function's doing. And then that can propagate throughout the rest of the program. So the Haskell people were able to use monads to mark the parts of the code that were doing I/O, and very cleanly separate them from the parts of the Haskell programs that were pure lazy. So it was a very elegant solution to the I/O problem in Haskell. And then they later on, after using it for I/O, found that monads could actually had a wide range of applications for all sorts of programming problems. So if you look at Haskell, you'll see they've got monads to do things like they have monadic parsers, for example. And what's another example? I was looking at a monadic web framework the other day in Haskell. Very interesting. So you can use them. They use them all over the place. I guess the point of telling you about this, though, is that, once again, if you start to Google for monad, often you'll see people writing about, well, monads, well, they're for doing I/O in lazy, pure functional programming languages. They're for doing I/O in Haskell. And it can be somewhat misleading. And you'll think, well, OK, well, that's not relevant to me. I'm using an imperative. I'm using an imperative language like C#. I don't need monads then if they're for doing that kind of functional I/O. So, but they have a much wider application. So monads are useful for a whole range of things. One of those things is controlling I/O in Haskell, but we don't really care about that. We're kind of more interested in the other things it can do for us as C# programmers. So I should have asked. I keep on saying C# programmers. Are there any F# programmers here? Most of them, OK, a minority. OK, right, that's enough waffle. Let's look at some code. No, sorry, you have to bear with me. I've got a brand new MacBook, and I'm still finding my way around it. Hopefully this will work. OK, so as I said, monads are great for doing function composition with monadic functions that return monadic types. And when I say function composition, it can sound slightly computer sciencey and scary, but in fact, as programmers, that's what we do all day. We compose functions into bigger functions, and then those functions into applications. So function application is simply just calling one function after another, or sort of putting them together so that we can call them together. So let's do an example of a very, very simple. I'm going to write a couple of very, very simple functions. Almost ludicrously simple. The first one here takes an int and returns an int after adding 2 to it. Yep. Now I'm using anonymous delegates here and lambda expressions simply for conciseness and to make this code sort of easier to read. You could do exactly the same thing with static methods, for example. OK. Let's have another function. Let's call this mult2. X times 2. OK, really happy with that. I'm just defining two functions. One adds 2 to a number, and one multiplies it by 2. Yeah. Now, if I wanted to call add2 first and then mult2 afterwards and build a new function out of it, I can do it very simply by just having another function from an int to an int and calling it. Let's call it add2 mult2. I'm very imaginative here with my names, you can see. And of course, it has to be kind of because of the function application. Where we do function application, it's all a bit kind of back to front. But there you go. Yeah. So I'm adding 2 and then I'm multiplying by 2. These are all really basic C# stuff. Yeah. Is everybody happy with this? It's this kind of thing we do all the time. So if let's try it with 3. So if I add 2 to 3, it's 5 multiplied by 2. I should expect 10 to come out. Yeah. So just to prove my point. OK, yeah. So there you go. So that's function composition. Let's write an amplified type now. I'm going to choose a type called maybe, a maybe of t for this, because it's quite simple, so I'll be able to do it in the time allowed. And but also but it has a little bit of kind of boilerplate around it, so it proves the point quite nicely. So a maybe is just like a null, but so we can use it with any type. It's not just limited to value types. So public class maybe t, and I'm going to give it it needs to have a value, so public t value, yeah, private, and it needs to have a property to tell us where it's actually got a value. Sorry about my typing. And rather than constructor, I'm going to give it a couple of sort of static constructor methods, one called just and one called nothing. Yeah, so public static maybe t just t value. Yeah, so this is going to just return a new maybe t with value equal to value, and has value, why isn't it like that, has value equal to true. Semicolons, the joys of public coding, that's what I need. Sorry, bear with me. Okay, and then another. And then just. No, maybe. No, nothing. And that can just return new, maybe t, with a value, or just use the default or whatever a t is, because we shouldn't be accessing anyway. And false. Okay, so there's our maybe value. So we've written an amplified type that just wraps a t, but can have no value at all. Yeah. Let's try and do a similar kind of function composition, but with functions that return maybe int rather than int. Maybe composition. Feel free to call out if you see me doing something stupid. Int, maybe int. So this time, a function from int to maybe int. Let's call it add2. Now, of course, it's perfectly valid to add 0 to 2. But in this business domain I'm describing at the moment, quite arbitrarily, I'm going to say it's not. So if x equals 0, then we're going to return a new maybe int nothing. Yep. Otherwise, I'm going to return maybe int just x plus 2. Okay, so it's almost exactly the same as the function we wrote above, except we've got this strange condition in there that if x is 0, we're going to return nothing. Yeah, I know it's kind of silly, but it makes the point. Right. And we'll do mult2, and have the same strange idea in there. Okay. Now, if I was going to use these two functions in a sort of in a kind of normal programming scenario, yeah, I might write something like this. So I'd write var a equals add2 to 3, yeah, Now, before I can use A, I have to test whether it's got a value, right? It might not have a value. Now that I know it's got a value, then I can run molt. Yeah. Var b equals molt to a value. And I can put an else clause in here. But do something else if it doesn't have a value. But the point here is that my maybe has boilerplate that always needs to go with it. Yeah? Whenever I use my maybe anywhere, yeah, I always have to check if it's got value first by having this conditional if A has value. Only if it has value is true can I say A value. So this is our boilerplate. It's not very much in this case, but it's there. And the exercise we're going to do now is to wrap up that boilerplate and put it away somewhere. So having proved that point, that's what we want not to see. Now, I would quite like to, oops, I won't do that. Do the same thing as I did with the simple composition. So doing add to and then molt to. So molt to, oops, molt to, add to, I've got the, you're supposed to shout out, Mike, you made a mistake. Okay. So it would be really nice if we could write that and just compose our functions that way. But of course we can't, because add2 returns a maybe int, and molt2's argument is an int. So of course you can't compose them like that. So let's write a function that allows us to compose them. Our famous bind function that we saw earlier. I'll write it as an extension method. Molt2. And if we have bind now, we can bind is a function that simply allows us to do that, to compose those two functions together, in the same way that we composed add2 and molt2 previously in the simple example. So let's to make my life easier, I'm just going to override the string on here. Override to string. Return, so has value, then I want to return value to string. Otherwise, I want to return nothing. Okay. Right, sorry, back to our example. Now I'm going to write some extension methods for maybe t. I could write them as instance methods on maybe, but I quite like that. I think it comes out quite nicely with extension methods. Static class maybe extensions. Public static. I'm going to write myself a to maybe first, even though I don't actually need it immediately. But, maybe to maybe it'll be useful. T this t value. Of course, here I'm just going to return maybe t just value. I mean, in effect, that just method on static method on maybe t is exactly the same. It is R2 maybe, so we don't have to write that. But it makes things come out a bit nicer further on. Right, now on to bind. Okay, so we want to write bind here, and this is the sort of crux of the matter, because this is where we derive that rather tricky looking signature for bind that we saw initially. So this is an extension method. So it's let's talk about its return type. Its return type from bind has to be a maybe int, yeah? Because it's the last thing that happens in this add2 molt2. So let's make that maybe int and bind. Its first argument is the return value of add2, which is also a maybe int, yeah?
Which one? Int or t?
I want int initially. I will make this generic later on, but I wanted to show it with int first, so that it's kind of everything kind of lines up nicely. I'm just going to call that a for no particular reason. Its second argument is mult2. Yeah? And as we can see up here, mult2 is a function from an int to a maybe int. Yeah? Let me just paste that in there. And I'm going to call that func for no reason at all. Have to call it something. Okay. So there we have. We've just derived the signature for bind, which is one of the two monadic methods, all just simply because we wanted to be able to combine those two functions together. Okay, so what does the body look like? Well, it looks like the boilerplate that we wrote just before. So we have to test whether a has a value. If it's got a value, we want to pass it to func from its value. Func, as we know, returns a maybe int, so that's fine. If it doesn't have a value, we want to return a maybe int nothing. Yeah. You see, we've taken that boilerplate code and we've put it in our bind method. And so now we can go back to here and we can use this for result equals add to mult2 3. I'll just do the same thing I was doing above, and we'll just output it. Now when I run that, I should see 10 again, which I do. So there you go. This is like we've gone a long way round just to get rid of a couple of lines of code, but this is the important point, yeah, because these can be arbitrarily complex. You know, maybe it's probably one of the nice simple things we could do, but you know, we can have amplified types with strange and wonderful superpowers and wrap them all up and then do function composition like this. So a couple of other sort of quick things I want to note. I can write bind like, not with x, I've already used that, z. Like that. This is interesting because it's in my expression where I'm doing the function composition. It means I've effectively got a handle onto the internal value of add2 of x. Yeah, I could do something here with z before passing it onto mult2. Yeah, it gives us that ability. So, okay, well that's a nice simple example. First thing, now I'm going to make bind generic rather than just dealing with ints, because that's not very particularly useful. If I say the input value is a b and the output value is the input value is a and the output value is b. Let's just change all those. So that's an input value a, and that's a function from an a to a b, and that's a b. Yeah. Maybe B. Okay, and this still works fine. Good. Okay, so that's nice. We've now written our first monad in C#. We've got our amplified type, our type with a single generic type parameter. And we've got our two functions, to maybe and bind. And there you have it. There's nothing more to it than that. It's a talk over. That's it. It's very simple. Okay, I'll just play with this a bit more now. Let's. So we're just dealing with ints there. I think it's quite an interesting example to look at how we can access the kind of the wrap values using bind by using kind of nested closures. And then play with them before returning them. So I'm just going to do a sort of silly example now. And I'm just going to concatenate a string, an int, and a date time. But they're a maybe string and a maybe int and a maybe date time. Yeah? So let's call this arbitrary composition. So let's have var maybe int equals maybe int just 5. Doesn't really matter what it is. We'll have maybe string equals maybe int just. Oh yeah, string. Yeah, thanks.
Can you use your extension method now as well that you've written?
I could do, yeah. So write 5 to maybe. Yeah, let's do it like that instead. It's quite nice. 5 to maybe. So my amateurish preparation for these talks is sometimes I do it one way and sometimes I do it the other way, and so I get confused in the middle. That's a hello to maybe. And let's have a maybe date time as well. Maybe date equals date time now to maybe. Okay, so I've got 3 maybe values. I mean, who knows where they came from? Somewhere in the guts of my program, yeah. And I want to play with them now. I just want to concatenate them. So I can do that using bind and kind of like and nested closures over bind. So let's say var result equals maybe int bind a value, maybe string bind b value. You can see each one of these is nested. Maybe date bind c value. Now I can internally I can concatenate them. String format. Oops, 1, 2, a value, b value, c value. And then I need to put it back to a maybe at the end, because bind is T to sort of A to maybe of B. And now if I get the result, run that, we can see the concatenation as we expected. So this is really nice now. We've got we've been able to play with our wrapped values. There's no boilerplate here at all. Yeah, no if statement saying whether it has a value, and no accessing that internal value. Let's just to prove that point. Let's create a nothing equals maybe. I mean, it can be whatever. Let's make it a grid. Nothing. Now I can drop this nothing anywhere into that. Anywhere in here, and the whole thing will shortcut and be nothing. Yeah. Let's put it here instead. So you can see that boilerplate code is still working for us. It's just we don't have to write it anymore. We've wrapped it up and hidden it away. And that's the kind of the real power of monads. They allow you to do that. Okay. Any questions so far? Right. So when people talk about monads in C#, the word link often comes up, language integrated query. I guess the point I want to make here is that there's no language integrated query here at all. We've just written some extension methods. I mean, you could do this with C# too, just as well. It would look pretty ugly, but you could do it. Link does provide some syntactic sugar to lets us use bind inside of the link syntactic sugar, but we don't need link in order to play with monads in C#. So I'll just show you how to do it with link. You've probably seen people do this before, but say we had, let's write it again, var, oh dear, where am I? Okay. Var result 2 equals from A in maybe int, from B in maybe string, from C in maybe date, select string format. Okay, sometimes intelligence really isn't your friend.
You're missing a semicolon.
I'm missing a semicolon. Oh, yeah. Thank you very much. I need one there as well. And then we can write out the result too. Except we can't. If I try and compile this, it'll complain. And the reason for this is that the C# team, when they designed Link, didn't use kind of the industry standard bind. They used it expects an extension method called select many instead. And select many is an interesting beast because it wraps up bind and to maybe. So I'm just going to write it quickly. I'm seeing a sea of red. Is that because of that? Let's find out. So select many looks very much like bind. So we'll start off by grabbing that, changing the name to select many, and it has a third type parameter, and it has an extra parameter there that takes a function from an A and a B and returns a C. I'm just going to call that select for no reason again. Don't get hung up on the names. And it returns a C. I don't know why everything's in red there. Is that because it doesn't like the generic nested class? I think. Maybe when I write it all will come up. Okay. We can write select many in terms of bind and has value. So let's do that. I'm not happy. Something's not good. Let me just comment out this for a minute. This keyboard. I'm missing a. Yeah. Oh, right. Okay. Yeah, missing a curly squiggly bracket. Brilliant. Thank you very much. That's good. Right. I should be able to put that back in now. I've learnt my lesson, not to have a brand new machine with an unfamiliar keyboard on the first. All the resharper keystrokes I try seem to have the opposite effect. Okay, so we can write select many in terms of bind. So we need to. The last parameter is a function from an A and a B to a C. Yeah. So we need to get hold of an A and a B, and so we can use bind to get the internal values of A and the return value of func. Yeah. So we've got the A there. If we apply func to that, that'll return our B value. So we can write bind. It'll return B value. All right. Now we've got A value. We can run select A value, B value. And then we need to turn it back into a to maybe at the end. Okay, so now we've got select many. Now this will compile and work, he says, hopefully. Yeah, there we go. So result 2 down here. Now, the really interesting thing is So we've introduced link syntax by adding. So link language integrated query works on a set of conventions. Yeah? It expects to find extension methods on your amplified types in order to work. These are written for you for things like IEnumerable and IQueryable, but you can write your own for anything. So in order to use from A in B, you need to write select many. There's a whole list of other extension methods you need to write in order to use other constructs in the link syntax. But this is to prove the point, really, that monads and lin syntax are orthogonal. They're not the same thing. Yeah, it's just you can use lin syntax to sweeten the syntax of when using monads, but link isn't. It's a monadic sweetener rather than being a monad itself. A monad is a simple amplified type with those two methods written for it. Okay, how are we doing for time? 20 minutes. Good. Now I'm just going to show you a couple of other examples just to prove. Actually, no, before I do that, note the signature of select many here. Remember we wrote it in terms of bind. I'm going to show you a couple of other monads, both based on types in the base class library, IEnumerable and task of T. And what we'll see is that the select many implementation looks identical for both of those once we've defined bind. So, enumerable monad. Okay. Of course, I don't really need to write this. It's just done as an experiment because it's already in the base class library. But if we were going to write to enumerable and bind, then we could do it like this. Yeah. So the boilerplate, whenever we deal with an IEnumerable, is a for each loop. Yeah. So effectively, we have a couple of nested for each loops to iterate round the A values in A and the B values that come out of the func there, and then you'll return them. Yeah. And we can write select many in exactly the same way. And note, this is identical, except we've got two enumerable instead of two maybe here. And there's an example of us using bind to do what we would do with, you can't see it there, but I'll kind of output a list of, so this, just move that up a bit. So here we're using nested closures with bind instead of link syntax to do exactly the same thing. So that's like from A and A values, from B and B values, select that concatenation. Let me show you task monad. Okay, so once again, we've got our two tasks at the top there. Well, we're just kicking off a new task. And bind uses the task continue with. Because func is, it's like a higher order function itself. So it's very easy to, if you've got an API that expects you to pass some, continuation functions into it, then it works really nicely with this because you just pass it in. You have to put that unwrap at the end there to sort of get you back to the internal value. Once again, look at select many. It's exactly the same. The only difference here is I've got to task here instead. And a really, really simple example, very silly example. We're doing the same thing again. Just, yeah. And we could write that from, from A and A task, from B and B task. We could write that using link syntax too. So you can see you can apply this to all kinds of different types. We could carry on. We could spend all afternoon sitting here just experimenting with different amplified types and seeing how we can play with them. So it's a very, very powerful pattern. Let's go back to select many. If I'm writing the same, I've got the same signature, and the same internals each time, isn't there an opportunity here to write something more generic? To write an interface, for example. Yeah. An iMonad interface with select many on it. You might think so, mightn't you? But in fact, you can't do it. The reason you can't do it is because we're sort of butting up against the limitations of the C# type system. Yeah? Because we can't, that's generic, but task can't be generic. Yeah? We can't say an M of A in C# where both M and A are generic. Yeah? So you have to write select many for every single monad you define. The nice thing is that it always looks the same. Bind's much easier to write than select many. You could just write select many yourself if you're just interested in using the link syntax, but I find it easier to write bind first and then that just is automatic. Okay. No, I'm going to find her. I want to go back to the slides. Okay, good. So that was an interesting example, just talking about the limitations of link and C#. So link syntax, it's designed for language integrated query. It's not designed for language integrated monads as such. Yeah? So it's quite limited in its application. You can use iterators to do something similar, but that comes out really ugly. I don't know if you go and Google for sort of monadic iterators, it really is abusing a feature that's designed for something completely different. I kind of understand that the async features in C#5 can also be used as a sort of generic monadic syntax too. But I'm not sure about that. It's something I need to look at a bit more deeply. At first, I thought they were confined to task of T, but apparently you can write a few extension methods and it'll work with any amplified type. Something to be investigated. But yeah, I mean, this is the core. We're butting up against the problems with the C# type system. And so every time we want to write a function that deals with monads, we have to write a new one for each monad. We can't write sort of generic monadic functions in C#, which is a shame. Okay, let's compare. Let's just look at F# and then Haskell and to see how they do similar kind of things. It's quite interesting. So F# doesn't have link syntax. It has these things called computation expressions. I know Haskell better than I know F#, unfortunately. So this was kind of my hacked attempt at doing this. But I think it's kind of I think it works anyway. So what we're doing here is we're defining the simplest possible monad. It just wraps a value. It doesn't do anything with it. Yeah? That's the identity A up there. And I'm defining a get value, which is like the value property on the one, our maybe we wrote earlier, and return, which is our to identity, and bind. Yeah. And this builder thing here is the class you have to write to work with these continuation expressions. So rather than writing a load of extension methods, you write this kind of builder class here and give it a couple of members. Once again, bind and return. It just does bind and return. I guess I could have written them in the line here rather than a separate thing. But and then you just new up a new instance of your builder, and then just use this sort of curly bracket syntax here, and this let bang. So this is exactly the same as writing from A in identity 4, from B in identity 3 in lint syntax. Yeah? Select A plus B. But it has lots of other control structures and things like loops and conditionals and stuff. It's much more flexible, and I think nicer in a lot of ways than the C# lint syntax, because it's not designed just for one thing. Once again, F# suffers from the same problem as C# in terms of its type system, as you can't define a monad in F#. It doesn't have those kind of higher order types. Haskell. Haskell does have higher order types. It does indeed define a monad. So here we are once again, we're doing we're defining our identity here. Haskell's syntax is very concise. I like it, but it can be a bit confusing when you see it for the first time. That's basically saying it's the same thing as our identity. That the A there is a generic value. I'm defining the get value property. And here, this is the really nice bit. I'm saying identity is an instance of monad. It's kind of the wrong way around, but that's how they do it. And return is like our to identity. And this crazy-looking operator here is the Haskell bind. Yeah? And the reason this is so concise is because Haskell has a very powerful type inference mechanism. And because we're saying this is a monad, the compiler knows what to expect here. So we're just saying, well, I'm just taking an identity and a function from A to identity, yeah, and then getting the value and applying it to the function. Haskell also has, just like link syntax in C# and computation expressions in F#, it's got its own sort of monadic sweetener. These do expressions here, so do here. This is just the same as from A in identity 4, from B in identity 3, select A plus B. Interestingly, the Java world is somewhat different from the C# world. It's the the .NET world. In .NET, we've got F# and C#, both of which F#'s more like a functional programming language with sort of object-oriented bits bolted on, I guess, more on C#, more like an object-oriented language with functional bits bolted on. But in some ways, the Java world's more interesting because Java is still very much an object-oriented language. It doesn't have nearly the same amount, the richness of functional features that C#. But they have Scala, which in some ways is a much more powerful language than F#. In Scala, you can define a monad. It's got a more powerful type system. So in Java, they're much further apart. You gain a lot more from making that jump from Java to Scala than you do from making the jump from C# to F#. Okay. Yes?
If you're working on Java,
Yeah.
I really recommend looking into Clojure.
Clojure too, yeah. Which is a kind of variant of Lispy kind of, it's a Lisp on JVM, isn't it? Yeah, yeah.
But the monadic things, that's pretty nice too.
Yeah, no, I haven't looked at Clojure. I should check that out, yeah. Okay, so just to wrap up, where next? I've got a series on monads on my blog, CodeRant. The Wikipedia monad page has got some good links on it. I originally got the whole kind of idea for this talk from Wes Dyer, who works on the C# team. If you look at this, the marvel of monads, you'll see that I don't have an original idea in my head, and I pretty much ripped off everything that he wrote on that post. If you're at all interested in this, and especially these functional programming, I would really recommend reading a good Haskell book. Even if you never intend to write a single line of Haskell in anger, it's very interesting because they have from that pure lazy point of view, leads you down some interesting rabbit holes, I found. Real World Haskell is a big, very comprehensive book. An excellent read, though. Learn Your Haskell for Great Good is probably a better starter. It's got some excellent chapters on monads and monoids and applicative functors and all these kind of things. I'd recommend those. Okay, done. Any questions? I've confused you all. Has it helped at all? Good. Well, I guess if there's no questions, we'll wrap up. Yep.